Hello Algebra 1 students, we are in Unit 3, Tier 3, Lesson 4a, Is it a function, real world that passes the vertical line test. So let's check off our booklet. Here we are in Lesson 4 of Tier 3, Is it a function, real world that passes the vertical line test. So here is a picture of something that we all use every day, which is our phone's charging. You know, it's at 5% and it's 9:02 on Friday, July 11th. So believe it or not, we can model a phone charge as a function. I shouldn't use this Cartesian plane, and for that I apologize, because its scale is not very good. If I would have done this correctly, I would have used something that had a scale similar to just the first quadrant, like that. We're never going to have negative numbers, so we should only have been in this quadrant right here if I would have thought a little bit more about it as I was putting the book together. But we can remodify this. Let's say this first dash is after 15 minutes, and this is going to be in minutes. And let's say the second dash is after 30 minutes. This third dash is after 45 minutes. Obviously, it's 0 minutes here. And then we're after an hour, and then we're at an hour and 15 minutes. And then the independent variable is the time, minutes. And then our dependent variable going up on the y-axis, that is going to be the amount of charge that we have. And let's say we go by, this is 10%, this is 20%, this is 30%, and this is 40%, 50%, 60%, 70%. Once we plug our phone in from 5%, obviously it's going to start right here at 0 minutes at 5%. But then as time goes on, it's going to gradually charge kind of on a constant rate. Right? So the kind of function that we see here on this graph is definitely a linear function, right? It'll charge at that constant rate until you take it off the charger. So this is definitely a real world function that would pass a vertical line test, which is charging your phone. Down here, again, I think I should have used just the first quadrant, which is this quadrant of the Cartesian plane. But, you know, I make mistakes too. So let's redraw our graph to only be the first quadrant. And we'll just kind of ignore the numbers behind like we did up on top. Now, this is a roller coaster. And a roller coaster going to a loop-de-loop, you would think, oh, well, that fails the vertical line test. But if you're talking about position, you know, our independent variable would be time, and then our dependent variable would be position. Or basically, when you're talking roller coasters, is how long has the ride been going on and how far is the roller coaster in its track or distance. So most roller coaster rides are only a couple minutes long. So maybe after 30 seconds, you'd go there. And then after 60 seconds, you'd go there. And then after 90 seconds, which is a minute and a half, you'd go there. And then after 120 seconds, it would go there. And then that's 2 minutes, and then after 150 seconds, we would be there. And then position, you know, maybe we'll be after 30 seconds, we'd be at, 50 feet down the track, then at 100 feet down the track, and then at 150 feet down the track, and then maybe 200 feet, or maybe these are yards. Let's call them yards. Position in yards. So again, if we were going to put this on a graph, we would see that after 30 seconds, let's say the car, obviously at 0 it starts here, but after 30 seconds, let's say the car is 50 yards down the track. Then after 60 seconds, it's 100 yards down the track. Then after 90, it's 150. After 120, it's 200. And then after 150, it'd be up here around 250. So if we again connected our dots, we would see that a roller coaster's position is also modeled by a linear function. So therefore, it would definitely be a real world function that passes the vertical line test. Good luck on your practice sets.